Welcome back to a new video about digital controller implementation. This is our example number 4. We continue with the Cascade implementation of our digital controllers. In this case, we will look at a third order system where we have the gain stage, a first order stage, and a second order stage, all of them in Cascade. And again, we have discussed that the Cascade implementation is useful when you want to reduce or make the sensitivity of the coefficient variations less sensitive. That is the idea of Cascade implementation. So let's see our example. We have the following transfer function of a digital controller given, which is here d is given by the controlling parameter over the error signal, which is shown here. You see it's a third order system. You see already it is given in the 0 to the power minus 1 variation, so you see the delays directly. So we would like to now have a flowchart of the digital controller to implement this, and then using a cascade of a first order and a second order transfer function to implement this controller. And of course we have also the gain stage, so that is another part of it. So let's see what we need to do in the solutions. We split the product. In this case it's already given in the 0 to the power minus coefficient, so we don't have to factorize and also divide by the exponent, so that is all not necessary here. So we just continue and then split the problem in the gain stage, the part of the first order, and also the part here, the second order. You can see that here clearly. You also see the coefficients directly here. So now we need to look at the gain, the first order, and also the second order. So step by step. The general first order transfer function we know also from our previous examples. Example number 1 specifically, let's call this D1, has 3 parameters, A0, A1 and B1. That's shown here. That's also the case for the second order system in a similar form, but that is of course larger. So we have then the C0, C1 and C2, and there is also D1 and D2 in the denominator. So we have our general expressions for the first order and second order transfer functions. And now we need to compare that with the transfer function given here and also use this D1 and D2 to make that cascade configuration. So let's do that. We start with the general expression and then I designated gain by a K here. You see the first order part from here, the second order part from here. Now we need to recognize the parameters like the A1, A0, B1, etc. So when I now make the product, which is then K times D1 times D2, that's just this. And now looking at the transfer function of the first order part, which is then 5 plus 0.8 z to the power minus 1 over the 1 plus 0.9 z to the power minus 1, that's shown here. And the second order part is this one, that's shown here, just a copy. Now we look at the coefficients A0, A1 and B1, that's just from here, you see that. And from the second order part you see 5 parameters, C0, C1, C2, D1 and D2. So we have now everything. So the only thing is we need to now look at the flowchart. So the flowchart of the first order transfer function, the stage 1 and the gain together is given by this flowchart in general. You see the gain part, and this is then specifically the first order flowchart. We have here the A0, the A1 and A2, B2 I mean, and we have the gain which is called K. Now when you now convert this using the values here and also the K, which is actually 6, so we can now say let's bring all the numbers here, which is then 6, a 5, 0.8 and 0.9. And again this z to the power minus 1 is a delay element, and that delay element depends on the sampling period. So if you have a sampling frequency, let's say 1 megahertz, then your sampling period is then 1 over that 1 megahertz, which will be then 1 microseconds. Okay, and again remember we go from error to the U signal. So in this case I have an in-between signal which is called the X, because I need to cascade the first order and the second order transfer function. I call this just X. So the next stage will be then the second order that will then start at the signal X and goes to U. So that's the next part, which is then the second stage, and then you can see that it started at X and it ends at U. Now we know this configuration for our example number 2, and we see also the general configuration, and you'll see now here 2 delay elements because we have z to the power minus 2 in the transfer function. Again we need to recognize here the coefficient C1 C0, C1, and C2, and also D1 and D2. So we need to place these 5 coefficients in here, and we know already them, just looking at it, just actually looking at the transfer function, compare that with the general transfer function. Now let's then bring the values here in this general flowchart. So we have now the 2 for the C0, 3 for the C1, that's all shown here, and then 4 for C2, and also for D1 and D2, the values are shown here. Now this is now the part of the second order transfer function flowchart. Now we need to bring them all together. That is the complete flowchart for the transfer function of the complete system. That is the gain stage. This was for our first order system. You see the in between signal X star, because we start at E, which is the error, and all the way to U, and in between we have this signal to designate the connection here. Then we go from X to U, that is then the second order part. We see all the parameters here. So that is actually now the cascade realization of a third order digital controller using a first order and a second order transfer functions in Cascade, and also a gain. Alright, this is our example number 4 about the digital controller implementation using the Cascade implementation of a third order system. In the next example, we will also discuss the parallel configuration, also move on to the PID controller implementation using this parallel and also the Cascade configurations. So see you next time in another video. Take care.